Okay. All right. Very good. So let's start this webinar, and we are very, very happy to have Filippo with us. Filippo Pecci is an associate research scholar at Princeton University, where they established a few years ago this Center for Energy Environment called the Huntington Center. And Filippo is a mathematician by background, did his PhD at Imperial College on computational optimization. So he's an optimization person. He's been working on water issues in the past, and then in the recent years, he's been moving his attention towards the energy sphere. Within part of his Zero Lab, which is a lab at Princeton University that some of you might have heard, because they've been quite influential, especially within the US, about modeling future energy scenarios and future energy systems towards net zero. And there, in that group, Filippo has been working on developing a suite of models, some of which are already available, some which are ongoing, and applying some of cutting-edge optimization methods and decomposition methods to solve very complex problems related to the energy sector. So we're very happy to hear your views today. And again, 40 minutes and plus 20 of Q&A. If there are immediate questions for comprehensions, I think of course, people here or online can also interrupt.
Of course. Thank you very much. Yeah, so I'm going to talk about developing a part of the work that we've been doing on developing the next generation of high-performance capacity expansion model for energy systems. This is work that has been done by myself and a PhD candidate at Zero Lab called Anna Jacobson. So I'm sure you're all quite familiar with this picture, but the need for a new generation models comes from the fact that with every net zero scenario, we will move from a world where a lot of energy consumption comes from different commodities like natural gas or coal to a world where a lot of it will come from electricity. And so we need electricity-centric energy system models where we have a high detailed representation of the electricity system because that's going to be connected to every other sector that we model. And in a collaboration between my lab at Princeton and other researchers at MIT Energy Initiative and NYU, we've been developing a multi-sector energy system model called MACRO, which stands for Macro Energy System Capacity Expansion Resource Optimization Model. We started from macro and then we worked out the other words, but it's going to be a high-performance, bottom-up, electricity-centric energy system model. So high performance means that it's built to exploit distributed computing through decomposition methods to really increase the computational capabilities of the model. And it's bottom-up, so it starts from the demand and the description of the technologies, and will build a capacity expansion model where we optimize capacity investments and operation of the system at the same time, with a detailed representation of different decarbonization pathways, for example, for industry. So a detailed presentation of different options for iron and steel production, or ammonia production, or cement production. And we also wanted to have a granular temporal resolution, ideally hourly resolution, with a full representation of the operational year, and possibly, well, actually, we needed to have multiple weather years considered to increase robustness. Macro will be open source, and it's being written with Julia and Jump. It's not available yet. It's under development. We started development almost a year ago. And also, we wanted it to be plug and play in the sense that it's flexible and can incorporate different sectors, and you can swap in and out different sectors without changing too much of the structure or anything at all of the structure. So in comparison to what we call the current best-in-class bottom-up multi-sector energy system model, we essentially, the main selling point for macro will be that it will have an improved computational performance that allows for a higher resolution. So if we compare to something like Rio, which is a commercial package, some of you might know, it's been used for many high-profile studies like the Net Zero America study or Net Zero Australia study. So Rio typically consider for the US 20 or 30 zones and uses 41 representative days for a single year. And from that, they then run the model. And as I said, it's been used for many high-profile studies, but the resolution is not very high. And so, and also it does not allow to include discrete investment decisions. So discrete investment decisions might not be very relevant for electricity, because for transmission lines, we can always have multiple transmission lines. But for big transmission lines, like DC lines, or for pipelines, if we are modeling natural gas or other commodities, then economies of scale really plays a role. And it matters whether the model thinks that it can build a 3.5 pipe or it can build either 3 or 4 pipes. And so having the ability to include discrete planning decision is a key when modeling multiple sectors. And the same for industrial facilities, right? We cannot build a 5.6 ammonia plants in Texas. There are 5 or 6. Similarly, other models here, I've quoted, I think, Massage, which has been used for several studies in Brazil. Similarly, they have only a selection of representative days. In this case, in this study was 12. It doesn't do discrete planning decision, and times is very similar again. So the idea, the need for macro is to achieve a model that can handle 2030 zones for the United States, for example, with hourly resolution for multiple years, and have discrete planning decision and have a solve time that is, less than 24 hours, because then with the model, we need to run a lot of sensitivity analysis. And so we really, it needs to run in as little as possible. So here is just a quick update on development status of macro. And the core structure of macro is complete. So the whole architecture is complete, and the whole mathematical description of different sectors is done, because it's very generic and can be applied to any sector. So if you have a model for hydrogen, you're gonna model a SMR. An SMR will have some unit commitment constraints and some ramping constraints. And those constraints are the same constraints that also apply to a natural gas power plant. So there is no reason for copying and paste the same structure everywhere. So we have a library of constraints that has been implemented already and can be applied to any type of resource. And this, we hope, will really speed up the implementation of different sectors, because users don't need, because modelers don't need to recode everything from scratch. They can use the existing pieces. So in the core structure of macro, we model a multi-sector energy system as a multi-commodity flow network, where we have nodes and edges. And these vertices, they can represent demand nodes, or they can represent transformations. So transformations moves a commodity into another one, or into multiple commodities. So a natural gas power plant is a basic example of a transformation. You will transform natural gas into electricity and CO2. But with this structure, we can represent every industrial plant, every type of process. And so we hope that it's general enough that we can use it to really model all the sectors that I've put there. And also we are building in a way that is designed for distributed computing. So it's being written having in mind that the main application for macro will be with the decomposition method. So if you don't want to use a decomposition method, you probably won't use macro. You will use some of the other models that exist, and that's perfectly fine. And if you are happy with the resolution they can give you. With macro, the idea is that you will use it to have high resolution models, and then you will use Bender's decomposition or other decomposition methods to really to enable that. So here is something I already said, but just some examples of what a vertex is. It can be a node, it can be a battery, it can be a demand node for hydrogen. A transformation can be like the red square. It's an electrolyzer. An edge can connect different vertices, and an asset is a collection of edges and vertices. So like in this case, a natural gas and GCC, it's an asset that has a natural gas edge, then electricity edge, and CO2 edge, coupled by the transformation. So the philosophy of macro is to have 3 different layers of users. There's going to be users who just interact with input and output files. So they don't need to know Julia. They don't need to know any like any actual mathematical equation. They just need to know how to build the input and how to interpret the output. And then we have a second level, which we call modelers. They need to know Julia. So they need to be able to write some code. They might be familiar with Python and can use Julia, but they need to have some programming skills, but they don't need to know, for example, jump. They don't need to know how you implement a constraint in an algebraic modeling language, because they can use the library of constraints that is already there. And so by doing this, what we have seen, for example, for China, I have a PhD student from Tsinghua University. He's implementing the iron and steel sector, and he doesn't know jump, he doesn't know mathematical optimization, but he knows the processes. And so by using the building blocks that macro has, he can build the whole sector. And then there are the developers, who are probably going to be very few people that actually implement new features or new constraints or new modeling options. And so they have to know Julia and jump and be familiar with the philosophy of macro and with the structure. But the idea is that the asset hides most of the mathematical complexity of the model. And so if you are a modeler, you just work on the assets. You don't need to know that there are vertices and edges and all this stuff. So hopefully this will allow for a lot of people to find macro useful. The general workflow in macro is to start from the input data, which is going to be in a combination of JSON file and CSV files for time series. And then slowly, you build the model, you load all the networks, you generate the model, and this is an optimization model that then gets solved. And then with the solution, you need to have some downscaling methods to unpack your solution, because you're probably if you do a study like a net zero study for the US, you're not going to represent every single industrial facility in the US. You will represent some aggregation of that. And so you need to have some downscaling methods to then represent those results at the final resolution. All this results in increasing computational requirement for the models, right? Because everything that I talked about having multiple commodities, multiple energy networks, having high temporal resolution, having a wide range of scenarios to improve robustness. So you want to consider different weather years, for example, for renewables, and having discrete investment and retirement decisions. So all these things will increase computational time very rapidly. And with the discrete investment decision, the increase becomes a non-polynomial, right? So we really cannot solve the model as it is. Even the best commercial solvers will struggle, as we will see, to solve these models. So we need to advance the computational methods in order to enable these high resolution models and make them useful. Typically, what modelers do, and this is something that probably some of you have also done, you work with a combination of either using different sampling representative periods to represent the system, or aggregating regions, or maybe ignoring or relaxing some operational constraints in order for the model to be computationally practical. However, these abstractions, they end up with, they come at a cost of a significantly reduced accuracy of the model. And so this might affect the then recommendation that we make out of the model, and the ability of the model to provide a real decision support for decision makers, whether it's industry or policymakers. So in this research that I'm presenting today, we move away from the standard practice of having some form of abstraction to simplify the model, and we focus instead on the computational methods to improve the computational capabilities of energy system planning models. So in recent work, it's based on, this is recent work done last year with Anna Jacobson, who is a PhD candidate at Zero Lab, and I have then taken it forward this year in a new preprint, which is currently under review. We developed new computationally efficient decomposition methods for energy models, where we can handle discrete investment and retirement decisions. So these are integer variables to capture economies of scale and achieve a runtime that grows linearly with the number of operational subperiods that are considered. So as you can see here, this is a plot from our results where you can see the runtime for a linear program, runtime should grow quadratically with the size of the model. So with the composition, we achieve a linear growth. That means that we can run a full year with 52 weeks. In this case, is 30 hours, but we actually do better later on. But this was from the first paper. And we can model multi-day energy storage and reservoir hydro resources and use linearized unit commitment decision in operational at hourly time steps. So we relax the constraint that the unit commitment variables have to be integers, and we assume them as continuous for the operation part. One can also then solve it with this linearization and then fix them or force them to be integers using the cuts computed using the linearization, if it's or using the same investment. So you optimize the investment decisions with a linearized unit commitment, and then you fix the investments, and you can optimize the operation with unit commitment if you need to run simulations for reliability. So how does this work? When we look at models, and this is common to all models, it's not only macro, it's not only GenX, which is the electricity system model we developed at Zero Lab, it's not only PIPESA or switch. Every model has this structure, and it looks like it's just a monolithic model with not structure, but actually by looking at it closely, we can discover some block structure, which I'm going to highlight here. So in these models, in energy system planning models, we have an objective that typically is to minimize costs, defined as a sum of investments and operating costs. And there is a little sigma there, which is the probability assigned to that week. So if you're doing like a multiple scenario analysis, you will have a certain weight assigned to a specific weather year based on previous distributions, and you can input it there. And then we have operational decisions. These are unit commitment states, power flows or energy flows, and this kind of operational decision like storage levels. And they are time series. They have hourly resolution. They can be, they can be grouped into operational subperiods, and those are represented by the index W. So the index W is the week. And if for a year, we have 52 weeks, so 52 subperiods. And then we have some other variables, which here I call subperiod linking variables. And these are like hydro reservoir storage levels at the end and the beginning of the subperiod. If you think about it, once you have storage, if you know the starting level of that week and the final level of that week is independent from every other week. Like if once those two quantities are fixed, the operation within the week does not depend on what happens on the other weeks. So we call them subperiod linking variables. And the idea here is that I want them to exploit this to design the composition scheme. And then we have planning decision variables, which again are fixed during the year. They can change with the different planning stage. So if you consider multi-stage planning problem, you maybe make decisions every 5 years. So you have, depending on your horizon, you have different investment decisions or retirement decisions that you make along the way, but they don't vary with the operation. They don't vary with hours, right? So they are also called complicating variables or coupling variables. They couple of hours together. The constraints are pretty standard. This is what is found in energy system planning models like PIPESA. You have some linearized power flow, so we don't do AC OPF, just a linearized power flow, ramping limits, and unit commitment for thermal resources and storage constraints. Those are all linear constraints. And then, as I said, there are these operational subperiod coupling constraints, right? That link storage level at the beginning of 1 week with the storage level at the end of the previous week. So they are represented there by that linear constraint. And then some planning constraints. Here you can have some minimum capacity constraints, for example, for certain resources. So the way, when we look at it, the way this looks like is a arrow-headed block structure where we have investment decisions that couple all operational periods, and also some coupling constraints like storage constraints that couple the periods. But then the individual operational weeks are decoupled once we ignore, well, we remove the storage and investment decision. And this is, as I said, it's common to many widely used open source models. So we started off from this block structure and designed the decomposition methods to exploit the structure and allow and enable high performance models. So in a standard Benders decomposition method, which some of you might be familiar with, but I will review it very quickly. In a standard Benders decomposition method, we treat the investment decisions as complicating variables. So we separate those from the rest of the problem. And we define two models: a planning subproblem, where we make investment decisions based on some approximation of the operating cost, and an operational subproblem where we optimize the operation of the system given those investment decisions we made. And the one thing we need to notice here is that the operational subproblem is a full year, right? It's a full year without a resolution. Here we have not decomposed the operational year. So it's very demanding to solve this model. And especially in a Bender's decomposition method where you do many iterations, that's going to be a problem. So what we did was instead, well, here, yeah, it's just a mathematical version of the previous plot where we define what the planning subproblem is and the operational subproblem is. So what we did was we included the sub-period linking variables like storage levels at the beginning and end of each period into the planning problem. So we treat them as planning decisions. And once those are fixed, then the operation of the system becomes decoupled in time. We can operate each operational week independently of the others because we are fixing all the sub-period coupling variables into the planning problem. So with this trick, now we are able to distribute the computation and the solution of each operational week over multiple cores. And this is what gives the advantage of this method. So you need to have computational power, and we are lucky in Princeton to have it, so it's good. The decomposition method iterates then between a planning problem where you choose the investment and a timing decision and these sub-period coupling decisions like storage levels, and an operational problem where you just optimize the operation during the week, and you can optimize those in parallel. So
what's the convergence between these two sub-problems compared to the standard methods?
So the convergence is the same, and the framework for convergence is the same as for standard Bender's decomposition method. It's just a different way of defining the planning and the operational subproblem. The solution of the planning subproblem gives a lower bound to the final optimal cost, and then you compute an upper bound to the optimal cost by optimizing the operation of the system for the investment decisions that you have made. And you iterate between the two until lower and upper bound are close, and you stop once they are close. So it's the same as standard Bender's. Here, the main difference. Does it take longer to converge? Or? Well, no, but we will talk more about that later. So it can take long to converge because these methods are known to suffer from instabilities, especially at early iteration. You can imagine here the planning subproblem makes decision investments based on an approximation of the operating cost. So at early iteration, that approximation of the operating cost is quite poor. And so you might make very weird, extreme decisions because you think that there is no cost in not serving electricity to a region because you don't have a representation of the whole power flow in it. So there are techniques that we apply to regularize the algorithm and avoid this extreme decision and enable fast convergence.
Can I ask something? So basically here you found the most clever way to divide up your model so that it can be parallelized. The key point is that there is very little ingoing and outgoing from these parcels that you... So in principle, if you had, for example, a whole sector that is not really linked to the other sectors, but as only, so if you look at the matrix of sector, you could single out sectors that you can also parallelize with the same idea in mind.
Yeah. Okay. So in principle, yes, all those sectors that will be a soft link, if they will be hopefully easy to parallelize and the convergence will be good. For sectors that are very tightly linked, the convergence will struggle more, right? And this is something that happens in decomposition in other domains as well, right? So yes, there will always be this issue. There is also another package called Plasmo, which is in Julia. It's been developed by colleagues at University of Madison, Wisconsin, where it's a general package for graph decomposition. And we are working with them to implement these in Plasmo, which then will allow us to treat with the same framework all different kinds of decomposition, both the spatial, sectoral, or temporal decomposition. But it's ongoing work. So I'm going to show some results now based on this first method that I talked about. We consider these four systems where we have different extension of the US electricity system in Gen X. with a single period planning model with hourly resolution. So we have 52 operational week with a CO2 cap constraints. And for this benchmarking, I'm only considering continuous investment decisions. So we will see later on what we do with discrete investment decisions. And this is a report, and you can find more details into the journal paper. But the main picture is this one, which I already showed, where we see that for those 4 different systems, the runtime with the decomposition method grows linearly with the increasing of number of weeks that you consider. So if you consider 2 representative weeks, 12, 22, 32, 52, then you get a linear increase in runtime by distributing the computation over multiple cores. So here in the 52 case, we are using 52 cores. Each core optimizes 1 week. And we can see that it outperforms a standard Bender's decomposition, where we consider the full operational year as a whole. The largest case that we were able to solve in 2 days with a standard Bender's approach was a 6 zone with 22 weeks. But we can see that the new method has a much faster convergence, both in terms of number of iteration and in terms of computational cost of each iteration. And one reason for that is also that we are adding, for each operational week, we are adding 1 cut to the planning model. A cut is a linear inequality, and it's the way that we communicate to the planning model how to improve the approximation of the operating cost. And if we consider a standard approach, we would add a single cut, so a single piece of information for each iteration. In this other distributed approach, we actually adding 52 cuts every iteration, so we add much more information. As we will see in the results later on, this method works okay, but still it can be quite slow in terms of number of iteration. And we saw that because we were still using something like 30 hours for solving a 52 weeks case. I said our objective was to go to less than 24 hours, right? So it's still quite slow. But we made further progress using something called level set regularization. There is a lot of maths here, but the main idea is that we take the solution of the planning model and those investment decisions that were chosen to minimize the total cost based on the approximation of the operating cost. And those solutions might be extreme, so we correct them by solving another linear program called a level set problem, where we look for a different solution that is nearby the solution that was computed by the planning model. And the definition of nearby is given by the level set constraint, where we say that we are looking for a solution that is only slightly suboptimal for the planning model, instead of being the actual optimal solution of the planning model. And this method is very common to regularize cutting plane methods like Bender's decomposition. And there are a couple of different choices that can be done to set up this level set problem. One is to use a L2 norm of the distance from your regularized solution to the solution of the planning model, the unstable solution. And the other one is to use the interior, to just look into the interior of the feasible set of the planning model. And we will see that that's actually the best option. And once we have solved the level set model, then we optimize the operation for this set of investment decisions that has been corrected. So we ignore the investment decisions made by the planning model. We only use it for the lower bound and to formulate the level set model. And then we just optimize the operation for this corrected version of the investments that are hopefully less extreme and can give us faster convergence. And we also now need to talk about what we do with discrete planning decisions. So if we relax the integer constraints on discrete investments, so we consider continuous investments, all the cuts that are computed along the way are all valid also for the integer case. They are still lower bounding the operating cost of the system. So we can just relax the integer constraints initially, run Bender's decomposition as if the problem was continuous, keep all the cuts that are computed along the way, preload them into the planning model, and now switch on the integer constraints and do very few. We see that this results in very few iterations to actually then converge to the integer solution, because we have already a lot of information on the operating cost of the system. It's being computed by sampling points that are not discrete, but it's still a valid approximation of the cost of the system. And so the planning model has a very good idea of what the cost will be. And so we do that, and we enable the use of integer planning decision.
Okay, yes. So does it mean that you basically have explored 0.9 and 1.2, and then you impose the integer strain, at which point it will take either the 0.9 cut of the 1.2?
Yes, and
you're very near.
yes, because the operating cost for 0.9 or 0.2 is not too different from the operating cost for 0 and 1. And so or for most resources, there will be some resources where economies of scale really has a big impact on the total operating cost, but the total operating cost of the system is not going to change too much. And so the approximation that you have built with the continuous investment decisions is going to be a good approximation for the discrete case. So if you know what the operating cost is for 0.2 and 0.9, you have a pretty good idea what will be for 1 and 0.
And these discrete are going to be, is there, as you were saying?
Yes, it can be that one. Yes, so if you're doing for lines, it's, are we building this line or not? For industrial facility, if the model is aggregated, it could be how many facilities are we building? How many nuclear plants are we building? Are we retiring?
And the models for not doing this integer, what do? They do scenarios like?
No, they then look at the results. At least for Net Zero America, I know what they did. They look at the results and then see whether they make sense and allocate the decisions based on what makes sense. So we have applied this regularized Bender's decomposition to a multi-stage electricity system planning model in the US, where we have 3 different planning stages. So we make decision for 2025, 2030, 2035. And each stage has 52 weeks. So we have 3 different operational years with hourly resolution and 52 weeks in each of them. And here we have 26 zones and over 1,000 different resources and 57 transmission paths. And for each path, we have 7 different line options that can be built with different voltages and different properties. So we really want to use integers to choose which one of those line classes is built and how many. We have a CO2 cap. And this model, you can generate it with GenX. And it will result in a huge optimization model with over 100 million variables. So even Gurobi, like the best commercial solver won't solve it because of many memory. So it won't even start. The Bender's decomposition that I just talked about, we implemented as a solver routine within GenX, and it's not released yet, but I'm working on it and should be released in one of the upcoming updates on GenX. So I first ran a benchmark with continuous investment decisions just to compare different options. Here we are comparing different strategies taken in previous literature. You have the slides, so you can also go check those papers. The DDDP is the dual dynamic programming. It's what is currently implemented in GenX. Was done by Derek Malapragada and others. And then I have a couple of other options. So I have the green line is Bender's without any regularization. So is our previous method from the previous paper where we didn't use any regularization. And then we have a couple of other options for regularization called L2 regularization, which I mentioned, and the trust region regularization. These were all looked at in recent papers. And you can see that the one that we are proposing in this study does the best. The one that looks at the interior of the planning model and picks a solution inside the interior space. So you don't need any, it seems that you don't need any clever objective function for the level set regularization. Just pick a solution that instead of being on the boundaries of the feasible set, it's an interior solution. And solvers like Gurobi will compute such an interior solution, call it probably an analytics center, and it's what gets computed if you don't put any objective function in your linear program. You don't put any objective function, run Gurobi, you will return the analytics center of the feasible set. And this is what I did here to get that point. And you can see that now we can solve that big problem. So it's 3 stages. our resolution, 52 weeks in each stage in 6 hours with continuous decisions. So that's a big improvement from before and from the other methods there. And you can see the impact of having regularization, because the green line and the orange line are exactly the same decomposition scheme, but one is not regularized. And you can see that the convergence is very slow. So here I've used a lot of cores. I've used 156 cores distributed over 6 computing nodes. So it's a caveat of this work, that if you use the composition, the way that you really get an advantage is by effectively using the distributed resources. So they need to be available.
So you solve the problem of climate change, but you create a problem.
Yeah. Yes. So for discrete decisions, what I said was we would solve the continuous relaxation of the problem to convergence, so the blue line, then switch on the integer constraints and run them to convergence. You can see that it takes very little time once we switch on the discrete constraint to converge. And I talked about that. So we were, with the disclaimer that we have used a lot of computing power. We were quite happy with the results because it's unprecedented to be able to solve a model this big in 8 hours, as far as we know. Another example I wanted to quickly show was with multiple weather years. So instead of having a different planning stages, we have a single planning stage, but we consider 8 different weather realizations, both for demand and availability of renewables. And here we consider electricity system in Brazil. This is an open source, open data model with hourly resolution. In Brazil, there are a lot of hydro reservoirs. So this was interesting because we wanted to see how the composition would do with a lot of hydro resources, because we are splitting up those storage constraints. And I ran a comparison with Gurobi. In this case, Gurobi was able to solve the model. So it did start and solve it in roughly 10 hours. And the decomposition methods run in 40 minutes. So this means that we could run a lot more sensitivity cases or MGA iterations with this method, right, compared to just running Gurobi. Or we could increase the spatial resolution. Here, the spatial resolution is not very high, and we could increase. We hope that this will give us enough computational bandwidth to increase the spatial resolution of the model as well. So I've talked about a lot of positives. I'm going to talk about some limitations. So first of all, macro is very young. So the code base is quite immature, and there is a lot of work that we need to do. We have limited demand side elasticity. So we have some way of modeling with flexible resources. But I think, we need better way to actually model consumer demands, especially with reference to buildings, heating and cooling. We don't have any global trade dynamic representative macro. So that's also something we are looking to build. We are talking with my colleagues at the Anderson Center. We might do something about that soon, but we don't have any connection to that, to global trade. We have a very basic implementation of lands and agriculture and water. So that's also something that it could be added. And the most important issue, in my opinion, is the lack of data. So we are trying to run studies in China and India, and you spend roughly 1 year building the data set, and then 2 months actually running the model. So the lack of database and open source database is really the main limitation to run useful analysis. The computational limitation that I mentioned with some of you already is that while runtime grows linearly with the number of operational periods, it still grows quadratically with the number of zones, so with the spatial resolution of the model. So there is definitely more work, and I'm thinking about ways now to apply and integrate this temporal decomposition with network decomposition methods to be able to deal with this quadratic increase in computational cost. And that's something that we are working on and thinking about now. And that's it for me. So I thank you for your attention, and yeah, we can discuss. Thanks.
Great. Thanks, Filippo, for the presentation. Maybe we start online if there are questions online that I don't know or I cannot see. Alicia, yes.
Hi, ciao, can you hear me?
Maybe you could.
No.
She cannot be shown. Okay. Yeah.
Okay, yeah, you can only hear me, not see me, I guess. It's all right. Hi, thank you for the presentation. It was very, very interesting. I have a couple of questions. The first one is, like, it seems like an amazing method. Would it be, what's the bottleneck to applying it to existing models? Like, it seems like what the idea seems to me is that the method for solving is very advanced and very like outstanding, very good, and then maybe it could be applied to other existing open source models in order to keep kind of the same model structure and then solve it faster if you want to increase the computational effort. And the second question is that if the fact that you're calculating, if I understood correctly, the storage levels are calculated in different steps, so in 2 different stages of the optimization, does that affect the solution? Does it give a different solution with respect to when you calculate it in a single step, in a single normal linear program? Yeah, thank you.
Yeah, 2 good questions. So for the first one, the mathematical structure of the model is the same as in both GenX, which is an open source electricity system capacity model, but also in other models like PIPSA and Switch. The bottleneck, I would say, is the availability of distributed computing resources. And with that, something that can be done is that we are talking with Google. They kind of promised they would make available something for users to run decomposition on, especially for NGOs. But it's a big limit. It's a bottleneck that we need to have distributed CPUs to run this on. But in terms of the model, the method can be applied to any electricity system planning model. They all share the same structure. For the storage resources, yeah, so the solution is feasible in the end. So it will satisfy the storage constraint. The way you make it feasible is either you include a big penalty for violating those constraints. So you pay a big cost, big operating cost if your decision doesn't satisfy the storage constraint. And in the end, at convergence, you want to avoid paying those costs, so the solution will be feasible. And the other option is that you implement something called feasibility cuts. So that when you pick a storage start and end levels that are not feasible, you generate another type of cut that's not an optimality cut, it's a feasibility cut that excludes that solution from new iterations, and you proceed with the next iteration. So there are a couple of ways for dealing with it, and yeah, and both are valid and they work, but it's up to the modeler to choose.
Okay, thank you. Very nice.
Yeah, Enrico.
Hi, very nice presentation. So I have a couple of questions. So the first one, so you mentioned that during the decomposition, you go from 1 operational year to 52 like weeks. Is this weekly resolution like a trade-off between computational efficiency or something else? So if you go like to 3 days or 10 days instead of 1 week, is there a difference?
Yeah, so it's 2 reasons. One is that if you go to 3 days, you need a lot more cores because so you have a sub-period of 3 days. So there are a lot more, well, there are twice as many sub-periods of 3 days almost in a year. So you need more cores. And the other reason is that in these models, typically, both PIPSA and GenX and Switch, you wrap the operation of certain resources around a week, well, around the sub-period. This could be like unit commitment, ramping limits, or short-term storage. And for example, for batteries, you see that you really need to have a period that is as long as a week to capture the variability in demand between the weekdays and weekends. You don't have this problem for like multi-day storage because like hydro reservoirs, we model them exactly like with the storage. But for short duration storage, we do have wrap around a sub period, and so we need to take that into account. If you use a sub period that is too short, you will miss out on some variability in demand.
And you also mentioned that you're modeling only one operational year, but if you have multiple consecutive years, can you still handle the situation? And is this sub-period, the weekly sub-period still good, or do you like?
Yeah, so here we model 8 different years.
But consecutive years or just
well,
8
I mean,
years taken separately?
I see. Yes, so you can model them as a consecutive years where you still have weeks that are consecutive, and then you're linking variables between sub-periods. They will link the last week in January, well, the last week in December with the first week in January of the next year. Or here, if you consider them as just as a scenarios, which is what I did here, you don't do that. So you cut the model at the end of 1 year and you start afresh and you start a new operation. So you can do both things. And yeah. Mm-hmm. I don't know what I mean, we need to see what the best, I don't know, from the modeling point of view, I don't know what makes most sense, but yeah, it should be possible with the method.
Okay. And I have another quick question. So those transmission lines are like real, or is that an aggregated from?
No, that's an aggregated model. So this is a model I adapted from an open data repository. And I think that's an aggregated. So you should think about those as transmission capacity constraints between regions. Like there is this much capacity that can go from there to there. So here I'm not doing integer constraints. I'm not doing integer expansion. I am just considering those as continuous decisions.
Oh yeah, makes sense. Thanks.
Yeah, thanks, Filippo. Very, very interesting, and especially very, I think, impressive improvement in terms of the feasibility and numerical solution. I have three comments or questions. So first one on this selection, forgot the exact name, this issue. I mean, looks a bit like this kind of near optimal solutions when you're also able to look at the kind of the cost differences from these. Looking at this kind of how far off these near optimal solutions are from the first solution you find, or
so let me just explain a bit better maybe. So the solution that we pick here from the level set problem, it's a near optimal for the planning model, and it's near optimal by alpha, and alpha is something that you choose. But then the algorithm stops only when the lower bound computed from the planning model and the upper bound computed from solving the operation model are very close, like 0.1%. So the actual solution in the end is optimal up to 0.1%. The investment decision that you try the operation on are alpha optimal, alpha suboptimal for the planning model. And alpha, in this case, typically with 0.5 works, but it's a parameter that you can tune.
Okay. Then another 2 questions before Laurent has another question. So on the extension and things, I think also a very list of future potential works, a lot of which is very relevant. One on the demand side, maybe. So you said it's kind of exogenous, basically. So which type is, let's say, the first thing you would go for because there's a lot of things like rationality. Yeah. I don't know if you have, like, for instance, for transportation, for vehicle choice, and so you have like, is there like some multinomial logic or something there, or that's something you can kind of connect to the model on the demand side without adding the complexity. So that would be basically possible to extend.
I think something about EVs and also about heating in buildings, like heating and cooling in buildings. Those options is something that I would go first with. Especially because we have a very, like, if you model heat and temperature as a commodity, like low temperature heat for industrial purposes, you can model that as a flow of commodity. But in buildings, it becomes much more complicated. So that's a main limitation, I think. And finding a way to represent accurately the demand in building and the hourly variation of it, it's something we need to address first.
Thanks. Laurent, I think.
Yes, thank you, Filippo, for the presentation. Yeah, I was just wondering to which extent, yeah, you can add other feature. I see that you cite lands, agriculture, water. So you can add whatever you want as soon as you stay in the linear programming world. So for example, yeah, if you had a land use agriculture model with a choice of crop, that would be possible. If you had a forestry model with forest management, and also if you can also think of adding materials, maybe with some process of stock of materials and stuff like this. So do you think all this development in some other direction would be possible and also benefit from the decomposition algorithm?
Yeah, I think, I mean, we have some representation of feedstocks for bioenergy, but it's not as detailed as you were saying. So we could model something, as long as the model follows the rule of being a graph, which can be represented as a graph, then we can model everything. There is a limitation on the runtime of the model. So we might, but one thing that we can do here is that we can change the resolution of the sectors, and we don't need to use the same resolution for every sector. So if a study focuses on certain aspects of certain sectors, we can have a detailed representation of those and a rougher representation of other sectors that are not as linked, as tightly linked to the model. But in principle, every sector that can be represented as a multi-commodity flow can be included, and we can apply the decomposition I talked about too. The issue is mainly with the increasing, if you increase the scope of the sectors, you will increase the spatial scope of the model, and so the model might be slow. And so there is more fundamental work to be done to solve this problem here. Yeah, instead of number of zones, you can think about number of sectors. The dynamic will be the same. So we need to find a way to solve that.
Okay, thank you.
No, but yeah, I was thinking, how do you solve that? But if a lot of things if there are a lot of input and a lot of output, which are connect the various zones, for example, then.
So, for example, we could use something like, we could aggregate the system within the algorithm. So the algorithm could use some aggregated version of the system, which is done in a way that you always underestimate the operating cost. So if you aggregate the system in a way that you always underestimate the operating cost, like you aggregate different generators and you pick as efficiency the worst, well, the best efficiency. If you do this aggregation, then you could compute some Bender's cuts for the aggregated model, and those will be valid for the full resolution model. And so that could be a way to deal with this situation where you have many connections, and so the decomposition might not work that well. And it's something that has been done in other frameworks, not for energy systems, but something that we could explore.
So basically, you're using an approximated problem to find the best points to solve the.
You could compute an approximation of the operating cost based on an aggregated model,
and then solve
the full resolution model.
But you start from a much better place.
So the solution at the end will be the solution of the full resolution model, but these essentially at each iteration we add those cuts. I don't think you can see it, but we add those cuts here. And this is what gets computed from the operational model. So we can compute other cuts, well, the operational model is not full resolution, it's an aggregated model, as long as we make sure that they are valid, so they underestimate the system cost. And so, especially at early iterations, you can get a pretty good idea of the total system operating cost, even with an aggregated model. And then you refine it as you get closer to convergence. So that could be one way to.
Okay, say that you have to convince me to pay you and all the course, etc., because it's, you know, to solve the problem in much less time, but with all this temporal resolution is so much important for. What would you tell me? What is the key? Why is it policy relevant that we solve it with weeks?
For policy, it's relevant because we risk of getting some decisions wrong. Like if you have a limited number of representative periods, you might not see variability in the renewables, or which are very important now for the energy system. And so you risk of choosing the wrong CO2 cap or CO2 price, because you're underestimating some variability, or you're misrepresenting some variability. And so having hourly resolution allows you to avoid that. And also something that is not maybe directly relevant for policy, but for technology evaluation, we do a lot of work on that at Zero Lab as well, especially for this long duration energy storage, which are coming on, and to really evaluate and assign a value to that, you need to really represent the system with hourly resolution, because they get value when there are the variations. So the bad year, when there is the bad wind day, it's when that long duration energy storage has value, right? So you need to have it in your model, otherwise you won't see the value.
Okay, thank you. I will give it to you, but there's online.
Hello, do you hear me?
Yes.
Okay, thank you. Yes, really interesting presentation. I wanted to go back a little bit to the land part. So first I wanted, if you could deepen a little bit more on how bioenergy feedstocks are currently represented, and also when you're thinking of potentially including land and agriculture, what are you thinking in mind? Like, how is the biomass being produced? Where is the biomass being produced? I don't know if you can deepen a little bit on this. And also because what I'm thinking is usually land use models work on a grid level. So they have, I mean, the grid could depend on the resolution that the model wants, but I've noticed that your spatial units are zones. So I'm wondering how these grids versus zones, if you have think about this, or what is the connection that you want to do?
Yeah, so first of all, in macro, we don't need to have the same spatial resolution for every sector. So we can represent the biomass sector as a single zone for the whole US, and the electricity sector with 5,000 zones. So the sectors, the resolution of the sectors is completely independent. So we can choose whatever resolution makes more sense. I think currently how biomass is represented is that we get a mapping from a region, which typically are states, to this electricity zone, which come from, these are mainly the electricity zone for different electricity operators. There is some intersection, weird intersection, but it's mainly that. So we map the state to, well, actually the county to the electricity zone. And then we have data for biomass in each county, which gets aggregated to the whatever level we want based on the choice the modeler makes. And then we have some regional supply curves that for each county, they give the price of a given, of a given flow of biomass, which depends on the volume. And so we have these regional supply curves to represent that price. This is a very basic representation of the biomass feedstocks, and we would like to instead look at, being able to model land use and agriculture with much greater detail. But yeah, I don't have the skills to do that, so we need help. So if you want to work on it, it would be great. And I think I answered both questions, right?
Yes. Okay. Thank you.
Thanks a lot for the presentation. Just like to understand the method, if you were to analyze, for example, a 3-year period, you'll need 156 cores to solve the problem.
Well, if you want to fully parallelize it, yes. You can do less, and then some sub-problems will be solved in series.
Okay, so you can wait. Like if you have 12 cores, to do 12
typically
weeks.
1 week solves in 5 minutes for this system. So you can also wait. And there could also be a scope for some, and this is something we thought about, and we have written a proposal for it, to use some machine learning method to predict which weeks have similar runtimes, so that we can distribute them in an intelligent way, so we don't waste computing power. Because here, a lot of the time, there will be a couple of weeks that are very difficult to solve, and every other course wait for those to finish. So there can be more intelligent implementations. We can do asynchronous implementation where we don't wait for every core to finish, or we can train some machine learning model to predict how to aggregate the weeks.
Okay. And how does it scale with the number of representative periods? I think you showed
so
this.
it scales linearly with the number of weeks, yes.
Okay.
Yeah.
Okay. Thank you.